Alright, so we're going to do organic compounds, and we'll get started. So an organic compound has carbon and hydrogen, and so typically we'll call these types of compounds hydrocarbons. Hydrocarbons, meaning that they have carbon and hydrogen. But you can also have other nonmetals. But essentially an organic compound does not contain any metals. There are organic compounds that bind to metals, like certain proteins. We call those organometallics. But you just need to be focused on these covalent nonmetal, but it has to have carbon and hydrogen. If it doesn't have carbon and hydrogen, we can't call it an organic compound. So for their properties, they're typically covalently bonded because, like I said, they're all nonmetals. They have really low melting and boiling points, and so think about why they would have low melting and boiling points if they are all covalently bonded. So we're talking about the intermolecular forces here, so think about that for a second. So the intermolecular forces that would have low melting boiling points would be your London dispersion forces. And so we're probably talking about pretty nonpolar substances. They're flammable, they undergo combustion. We know a combustion reaction is a carbon-hydrogen compound plus oxygen makes water and carbon dioxide. And then they're not soluble in water, meaning that they're likely nonpolar, which we also understand from those London dispersion forces, those low melting and boiling points. And so we can really bring together what we know about compounds into understanding these properties of organic compounds. So organic versus inorganic. We've got sodium chloride on the right. And so we have the sodium chloride. As you can see, sodium chloride is formed, not necessarily molecules, but this formula unit. And it is a 1-to-1 ratio between sodium and chloride ions versus your molecule of propane here. And so propane is going to be a molecule of 3 carbons and 8 hydrogens, and then each molecule has its own individual particle, versus a formula unit is kind of like a big crystalline solid. So some properties of organic versus inorganic are here in this table. So if you're interested in looking through this, we can look at the polarity of the bonds. We can look at their melting points and boiling points. Ionic is going to be really high, and then you've got your nonpolar covalent, which is going to be pretty low. You've got your flammability and your solubility in water. And so when we're talking about hydrocarbons, we're actually going to be looking at a few different types of models to study this. And so the first type of model that we're looking at here in A, this is called a space filling model. As you can see, it fills up all the space. This is the most representative of what the molecule actually looks like, but it's a little harder for us to look at that and tell what's going on. So then we have a ball and stick model. As you can see here, you have a tetrahedron, and we have that 109 angle. Here is your wedge dash model, which you're familiar with. Here's your typical Lewis structure, also known as a structural model. And then here you have your molecular formula. And this is for methane. And we know methane is CH4. That's one of the common names you need to know. We're going to learn how to name that with the organic naming system in just a second. But I wanted to highlight just what a saturated hydrocarbon is. So a saturated hydrocarbon, all the molecule has single bonds. So it is totally saturated with hydrogen. It has as much hydrogen as it could possibly hold. Every carbon has 4 lines, each one designated to a hydrogen. If you don't have that, you would have an unsaturated hydrocarbon where you don't have all single bonds. So for example, if I look at this molecule, this is called ethene. I have 4 lines around my carbons, right? But this line right here, oops, this line could be bonded to a hydrogen here or bonded to a hydrogen here, but instead it's bonded to the carbon. So it's twice bonded to the carbon, which means it is not as fully saturated with hydrogen as we could possibly make it. So that's unsaturated. So that's what they're talking about when they say saturated versus unsaturated fats. Our next molecule we're going to look at is ethane. And so what I want you to notice as we look at these is that, remember we had methane, and the what do you notice about the names of these organic compounds? Right, the ending is ane. And so that ending ane means all single bonds. And so an ane ending, let's make that lowercase because that is going to be true, means all single bonds. And we're going to look at this a little more in depth later. That is called an alkane. So the organic compound with all single bonds is called an alkane. And then we have this prefix, eth and meth. So methane, if you remember, has how many carbons? Right, methane is CH4, 1 carbon. Ethane has 2 carbons, and it is saturated. If it's all single bonded, it is saturated. So we just kind of fill up each carbon with as many hydrogens as it can hold, and so that would be 6 hydrogens that I can hold with to maximum value. And so how can I tell how many carbons are in my alkane? Here are your prefixes. And so we have all the prefixes 1 through 10. So this is for the number of carbons that you're looking at. And this will help you name and write the chemical compounds. And so make sure you know those. Most of these are pretty similar to covalent. The first 4 are not. So this is meth, eth, prop, bute, not but, bute, pent, hex, hept, oct, non, and dec. And then we'll put an ending on it in a second once we look at the different types of organic compounds, functional groups that we have. And so here's some names, the first 10 alkanes. And so you've got 1 carbon atom, this is methane. This would be ethane. 3 carbons, do you remember, was propane. This would be butane. Then we have pentane, hexane, heptane, octane, like in gasoline, nonane, and decane. And there are a few different types of these structural formulas. I'm going to show you a little bit more of these, but I do want you to look at these condensed structural formulas. You're going to need that for your experiment, and the line angle structural formulas, we'll talk about that in a second. But a condensed structural formula is kind of like a Lewis structure, but instead of drawing out the bonds to all of the hydrogens, we are just showing them like connected to the C. Like I understand this as all single bonds, so I don't need to draw out every single line to a hydrogen. I can just like say, hey, this carbon has 3 hydrogens attached to it. Hey, this carbon has 2 hydrogens attached to it. And then you kind of can get the idea, draw it from there. So it's just a shortcut. But I do show the bonds between carbons in the condensed structural formula. And so let's look at alkanes. You're going to be studying only alkanes for your experiment 13 and 14, and so we'll have more than that you will need to know, but you won't be responsible for them on the experiment 13 and 14. So it's just alkanes for the first part. So this is propane because it has how many carbons? Right, it has 3 carbons. So if I were to write this, it would be C3. And then how many hydrogens can this have? This is 1, 2, 3, 4, 5, 6, 7, 8. So H8. That would be the symbol. You just count it up. That's the molecular formula for propane. And so the first thing that we're looking at is the condensed structural formula. Like I said, we're just going to kind of collapse these 3 bonds, and just kind of write, hey, you've got 3 hydrogens around that carbon. And so we can not have to draw all of that out. If you have only 2 hydrogens around the carbon, we just say 2. And then you also show all bonds to other carbons. The line angle formula is probably the most condensed. It's not called condensed, but it is the most efficient way of drawing these. So what this means is that every end and every joint, okay, every point or every end is a carbon. And then we're just assuming that it's filled up, totally saturated with hydrogens. And so if I wanted to go in and kind of figure out how many hydrogens I have, let's look at the carbon on an end. On the end, the carbon will have 1, 2, 3 hydrogens because it already has 1 line here. Every carbon wants 4 lines. This carbon has 1, 2 lines, so it would need 2 hydrogens. Again, in the middle, you've got 2 hydrogens hanging out. And then on the ends you have 3 hydrogens. And so if we take this and turn it into a molecular formula, or let's do a condensed formula first. And so this first carbon is a carbon with how many hydrogens? Right, 3. Then we have a bond from one carbon to the next carbon, so we do write that. And then this carbon is CH2. And then we have a bond to the next carbon, which is CH2 as well. And then CH2, and then CH2, and then CH3 on the end. So pause really quick and give me a name for this alkane. So this is 1, 2, 3, 4, 5, 6 carbons. The prefix for 6 is hex, and this is all single bonds, so it is an ane hexane. So here's some structural formulas for butane. Notice that when I do the expanded structural formula, this is the same as your Lewis structure. So if I look at this expanded structural formula, I have these condensed structural formulas that go with it. These are all the same. And so when you're looking at your experiments, you're going to have to draw some things that are different. These are all the same. And so if you were to look at the longest chain of carbons that's not breaking, you see that we have 1, 2, 3, 4 carbons, so that's butane. This is 1, 2, 3, 4 carbons, butane. 1, 2, 3, 4 carbons, that's butane. 1, 2, 3, 4, butane. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So it doesn't matter how you draw it, the longest chain of carbons is still 4 without breaking any of the carbons off and putting them somewhere else or branching them. So this is all still butane. It doesn't matter how you draw it. You could draw it any of these ways and it's the same thing. Line angle, we have 1, 2, 3, 4 carbons, or you can go down as you begin 1, 2, 3, 4 carbons, again all still butane. So there's just many ways that you can draw the same thing. So don't get confused if you see a structure that is a little bendy versus straight across. It can still be the same compound. It's just that you're just drawing it a little wrapped around or kind of bended. We also have cycloalkanes, and so like the name cyclo talks about, it would be a circle or a cycle. And so cycloalkanes just have less hydrogens than you can have because every carbon is an interior carbon. If you look at this, you'll see. So propane has 3 carbons, right, in a straight line, unbreakable chain, or unbroken, unbranched chain here. And then you have 3 carbons in a circle here. So this is cyclopropane. But if I'm in a circle, I cannot have these 3 hydrogens on the outside because I'm taking up a bond space to bond these 2 together. And so this is not a saturated compound because it does not have as many as it could possibly have, as many hydrogens as it could possibly have. So if you see cyclo, just put it in a circle. Some common cycloalkanes and how they're drawn. You can see how the line angle formula is really easy to kind of see. Remember, every single corner is a carbon, and so you can kind of use that to guide you. and then every carbon has as many hydrogens as it can around that. And so here's some images of the some common cycloalkanes. So a structural isomer, remember iso means the same. So what's the same about a structural isomer? It has the same molecular formula, but it has a different structure. So it's set up differently, but it has the same number of carbons and hydrogens. So let's look at this guy. This one is 1, 2, 3, 4. So this would be a butane, right? And so I'm looking at C4 and then count my hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and so H10, and the other two structures for that. Now let's look at this one. How can I name this this compound? Well, I'm always going to name starting with the longest chain that is unbranched. So I need to look at the longest chain. So my longest chain options are 1, 2, 3, or 1, 2, 3, or 1, 2, 3. Every option of this gives me a longest chain of 3. So let's just highlight my longest chain here. 1, 2, 3. It doesn't matter which one I choose. So longest chain means this is going to be a propane. So already it has a different name. So we're looking at different structures and different names for this. But let's look at the chemical formula. C, how many? 4. And then let's count our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the same formula. We're not quite done with the name though, so let's look at the beginning of this. It's not only a propane, so I have to think about, I'm going to name it a little bit differently. I'm going to put what I call a substituent group. And so I have this side chain kind of hanging off here. Do you see that guy? This side chain is a number of carbons. And so that number of carbon is 1. So 1 carbon side chain. And so what's our prefix for 1? Meth. And if I have a side chain, I put a little ol on the end to show that it's not a methane hanging off. It's a methyl like group hanging off. And so I'm just going to write as methyl propane. And we can label where that methyl group is. For this one, you don't have to because there's only one place it can be. If you take this methyl and you put it on this carbon, you just make butane again. Or if you put it on this carbon, you just make butane. So it can't be on carbon number 1 or 2, or 1 or 3. So we're going to number our carbons here. This is 1, this is 2, and this is 3. The methyl cannot hang off 1 or 3 because then it would just be like adding on to the longest chain. So the methyl has to hang off carbon 2. So we can say 2-methyl propane. But again, you don't have to say the 2 in front of it because there's only one way that you can have a side chain on a propane, right? It has to be in the middle. So let's look more at like how to name these substituent groups, these side chains. So if we're looking at just looking at our total suffixes, we know we've already talked about alkanes. If you have a double bond somewhere, that's called an alkene, so we name it an "ene" at the end instead of "ane." So like ethene, like that you saw in the beginning. That means 2 carbons with a double bond in the middle, surrounded by its hydrogens. And then if you have an ine, that is a triple bond. And so if we wanted to do ethine, that would be a triple bond linear structure. Now if we will have some side groups, like we just saw that methyl group. You may have a halogen as a side group. So if you have a fluorine, you call that fluoro, chloro, bromo, or iodo, depending on the halogen. If you have a carbon, we say the number for the prefix plus an ol ending. For example, methyl is a side chain or a functional group of 1 carbon, or ethyl would be 2 carbons, propyl would be 3, etc. So look at here's some, don't worry about any of the common names. So this iso, sec, tert, we're not really worried about that. We're going to name it only with one style, not with the common names. So this is just showing you some of these different types. If you're going to 2B, you will have to know iso, sec, and tert, but for us, you don't need to know that. So we're only looking at the longest, the side chain number of carbons here. Haloalkanes are halogens with alkanes, and so don't worry about the common names here. Only the IUPAC names, which is just the formal naming system we've been using for the whole class. So chloromethane, bromoethane, 2-fluoropropane. Okay, so look at this name. It's a propane, so it means it's all single bonds. It's 3 carbons. It has a fluorine on carbon number 2. Look at this one. This is a propane, so all single bonds. The longest chain is 3 carbons. Let's identify this longest chain. Here it is. It has a methyl. Where's the methyl? Carbon 2. Here it is. 1, 2, 3. It has a chloro. Where's the chloro? Carbon 2. So the name is telling you exactly where everything is on that compound. So some more functional groups that I want you to know. Again, these are going to be multiple choice on the final exam. And so if you can just recognize it, you can say that functional group exists. An alkane is single bonds. Alkenes have double bonds. Alkynes have triple bonds. An alcohol has an OH, okay, and it ends in all. An ether has an O in the middle, an oxygen in the middle, and R just means some other carbon stuff. So imagine there's just any other carbon stuff there. So R equals carbon stuff. Okay, it's just the rest of the chain of things. Don't worry about epoxides. You do need to know haloalkanes and ethers, alcohols, anes, enes, and ines. An aldehyde is carbon with a COH at the end. So C, and then with an OH at the end. A ketone is like an aldehyde, but instead of a hydrogen, it's got other carbon stuff on the outside. And a carboxylic acid has 2 oxygens bonded to a carbon with an OH at the end. Don't worry about anhydrides, esters, amides, or acyl halides. If you just know, at least I would say if you need to like only know a few of them, just know the top of this chart, and then you can probably process of eliminate any of the others that you don't see. I would know carboxylic acid, and aldehyde and ketones are pretty much the same thing, except you've got a hydrogen versus another R group. And so I would just maybe make a few flashcards with this, just to kind of recognize the shapes. And then again, it's only going to be maybe one question where you need to know these on the final exam, and a lot of times if you know some of them, you can do process of elimination until you can like, okay, well I know a carboxylic acid is COOH, I don't see that here, so I can cross that out, right? So even if you're not sure of all of them, let's just get some of them in practice and look at them a little bit, and then you can eliminate those. I would say though, our work is going to be mainly on alkanes and haloalkanes. So properties of alkanes, like we said before, they have dispersion forces. If you're branched, you have less intermolecular forces because you can't really stack on top of each other. If you're kind of in a straight line, you can stack, and so that gives you more opportunities to like attract together. And so the cycloalkanes are the kind of the opposite. They have more places to connect because they're typically kind of flat, and so you can have stronger forces. Stronger forces meaning higher melting and boiling points. I'm not really going to ask you so much about the properties. You just need to know how to like write and name them. So looking at boiling points again, you can check out the properties on your own, but you shouldn't be asked a question about the specific properties. They're going to focus more on writing and the naming of the compounds. So here's just an example of what an alkene and alkyne would look like. I want to go ahead and practice just naming these. And so pause and see if you can try to name these, and then unpause and we'll go through it. So look at this one. Let's first start at the end of our name. So the end of the name is going to be ein, een, or ein for most of the things we're using. This is a triple bond, and so this is an ein ending. Now, how many carbons do I have? Because that goes in front of ein. I have 2 carbons. And so the 2 carbons here are going to be ethine. And that's it. There's no other functional group. It's just carbons and hydrogens, nothing else fancy hanging off. You don't have to tell me where the triple bond is. There's only 2 carbons. It's just in between the 2 carbons. There's only one place the triple bond can be. But if you're looking at the second structure, there are a lot of places the triple bond can be. So you do have to tell me where the triple bond is. And so the first thing we have to do is find what I call the main chain, which is your longest chain. And so we kind of have to explore all possibilities of the longest chain. So we can go 1, 2. Now remember, on either side of this triple bond has to be a carbon. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's an option. Come on. 1, 2, 3, 4, 5, 6, 7. Okay, well, I'm not going to do that one because 8 is longer. 1, 2, 3, 4, 5, 6, 7, 8. So I have, oh, and there's another option. So let's go. That one's long enough. 1, 2, 3, 4, 5, 6, 7. Oh, that was the same one. So we have 2 options. We can either go this way or we can go this way. Now, what do you think is more important? To have the triple bond in your main chain or to have the triple bond in a side chain? It's better to always have your functional group in the main chain. So try to put your functional group in the main chain. And so we're going to choose this as our main chain. And so our main chain is 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's oct. And we have a triple bond, so that's ein. Again, we're going to start at the end of the structure and work our way forward. So now we have to examine our side chain. So our side chain is 1, 2, 3 carbons. Oh, I'm sorry, hold on, back up. And before we do the side chain, you have to tell me where the triple bond is. So we have a couple of options to number our carbons here. So we can number our carbons 1, 2, 3, 4, 5, 6, 7, 8, or we can number them 1, 2, 3, 4, 5, 6, 7, 8. So do we want to say that our triple bond and our side chain are on carbons 1 and 4 or 5 and 7? Those are our options. So our options are 1 and 4 or 5 and 7. Choose the lowest number carbon for special groups. So that's just for side chains and for any double or triple bonds. And so we've got, I'll write this down here, we've got our octine. And so now we're going to look at our side chain. Oh, sorry, we're going to say where our triple bond is. We're going to choose that our triple bond is on number 1. Right, that's the better option. And so we say 1 octine. So here's a special thing. Where is that special thing? The special thing is on carbon number 1. It could be carbon number 7 where it starts, maybe moving this way. But it's better to call it number 1. So that also means that my side chain gets to be hanging off of carbon number 4. So 1, 2, 3 carbons. We don't count a carbon twice. So this carbon is already in the main chain. We don't count this carbon. So 1, 2, 3 carbons. And so that's going to be a propyl group. And where is it hanging off? it's hanging off of carbon 4. Because we've chosen that way of numbering, we have to stick with it. So this whole name is 4-propyl 1-octene. Okay, so break this down, start with it at the end, kind of make it like a puzzle to kind of solve. Okay, so here are some other common names, or comparison of the names. Don't worry about ethylene and acetylene. We're not going to use those common names. Aromatic compounds are essentially compounds that give off lots of smells. Because they have a special structure. So this special structure here is actually a benzene. And so here's what benzene looks like. And a benzene is a cyclohexane. Okay, so 1, 2, 3, 4, 5, 6 carbons. And it has double bonds every other carbon. So you can actually draw a resonance with this, where you could draw your double bonds either way, and it's correct. So I kind of can't choose between these two, and so what happens is the electrons in here actually kind of hop around to both places for a double bond. And so we just kind of put a circle here to show that there's this rotating electron circle happening, moving around all these double bonds in here, because each of these double bonds is an area for electrons to kind of hang out. And so we can kind of shorten this by just drawing a circle instead of drawing all of this. I just draw this or this. And those electrons being fluid to move around cause the substance to have more of a smell a lot of times. And so electrons moving around can cause a substance to light up, or it can cause a substance to emit an odor. And so that's just an interesting little tidbit. You should just know what benzene is. So you should know that when you see a cyclohexane with double bonds or this ring in the middle, that is benzene. That you don't need to know any of these compounds. Just recognize, oh, it's got a benzene. If you can look at this one, what is this? An O in the middle with two things hanging off of it? Right, that's an ether. Right, so that's an ether group. This right here is an alkene, right? And this right here would be a alcohol. Now, an alcohol hanging off of a benzene is a little bit different, but if you can just recognize, like, oh, that's an OH group, that's probably an alcohol group, that's fine. So your experiments 13 and 14 are going to be kind of like study assignments, so just practice them, try to kind of get as much as you can, send me images, and work together, and then you can resubmit them as many times as you need to kind of make that work. And so good luck on that, and I hope that this helps. There's some more videos in Canvas for you to kind of go through some more practice, which I know this presentation didn't give you very much, but that's it for what the book kind of gives us. So I will see you guys later. Have a great day.